Bismillahirrahmanirrahim. The topic of induction motor continues, and this question is related to calculating the efficiency and the power flow in the motor. So, I would like to briefly shed some light over the topic of power flow in the induction motors. So, to understand how power is traveling, we have been developing and using the concept of power flow diagrams. So, the power flows in the motor. At the input side, we have for the motors, we have electrical power, and P input we can say for the motor, we can write for a three-phase motor Vt IL cos of theta. This is the input power. Now this is the electrical power that is being used by our motor. This is the motor, and this is the electrical P in. So this power is being used. Now what is happening to this power? What are the fundamental losses? And finally this P in is converted into P out. This is the mechanical power. So let's look at this. What will happen is, first of all, we will be having our stator winding. We will have stator copper losses. We will lose the power in the stator. After this, we can lump here the core losses for the magnetization effect. And once these two losses are removed, then the power travels through the air gap inside the motor. We know that if this is the stator, and here we have the rotor. So the first two losses are happening in the stator, and then the power actually the rotating magnetic field cuts the rotor. So there is a power that travels from the stator stationary part to the rotor through the air gap. So we can call that power as air gap power, or power that flows through the air gap to the rotor, from the stationary part to the air gap to the rotor. And after this, we will have the voltages. The field will cut the rotor, the voltage will be induced in the rotor, and there will be electric current that will flow in the rotor winding, and that will result in rotor copper losses. Okay, rotor copper losses. Again, it is still the electrical power. We have not converted this power into mechanical power up till now. So first, the power entered the stator. There were losses in the stator winding. There were also magnetization losses, eddy current losses, hysteresis loss, core losses. And from then the power traveled through the air gap and got induced over the rotor. It is still electrical phenomena through the induction. Power is lost at the rotor. And once the power is lost rotor, then we can say that the power is now converted. We can see the power converted. That means that electrical power is now converted into induced torque, into that is P electrical is now converted into mechanical power. And after this conversion, we will have our famous friction losses, friction and windage losses. That are the mechanical losses, friction and windage. We can say we can lump stray losses here. And then at the output of this machine, we will get our output power, which is actually equals to low torque into mechanical speed. So this is how the power flows inside an induction motor. Now let's come back to our question, and it is talking about, we have a 480 volts which is actually our 60 hertz and 50 horsepower motor, induction motor, that is drawing this much current and this much power factor. The stator copper losses, we have stator copper losses. They have given us stator copper losses, and the rotor copper losses are also given. The friction and windage losses are also given. The core losses are also given. And the stray losses are negligible. No need to consider them. Now, what in these types of question, they give you few powers, and then you have to calculate the powers either by the basic formula or by subtracting the power. So the first thing is, what is the air gap power? Now we know that air gap power, the power that is present at the air gap, is actually equals to P in, the air gap power will be equals to P input power minus stator copper losses minus core losses. These two losses, when we subtract, we can calculate the power at the air gap. So let's look at this. Now, can we calculate input power to the machine? Yes, we can. They have given us the terminal voltage, they have given us the line current, they have given us the power factor. So we know that P in equals to, for the 3-phase input power, is under root 3 Vt I of L cos of theta. So Vt is actually 480 volts. I of L, they have given us 60 amperes. Cos of theta, they have already calculated for us, and that is 0.85. So the input power into the machine is now 42.4 kilowatt. So if you look at here, this is actually 42.4 kilowatts. How have they given us stator copper losses? Yes, they have given us stator copper losses. Where there are, let's look at this. This is 2000 watts or 2 kilowatt. Have they given us the core losses? Yes, they have also given us the core losses. It is 1.8 kilowatts. So once we have these values, we can calculate air gap power, that will be equals to 38.6 kilowatts. So this means in a real motor, the power that entered our machine and was a part of it was lost, and the power that traveled through the air gap and got induced over the rotor is this much power. Now the second part is about, let's see, the power converted. So what is meant by the power converted? The power that was converted to the mechanical power. That is the part where the magic of a conversion takes place, at this part. So what is power converted? It is actually air gap power minus the rotor copper losses. So if they have given us rotor copper losses, yes, they have given us, so we can easily calculate this. So this is actually a very simple question, and it is not very confusing if you understand the basic concept and you know the power flow diagrams. So air gap power we have calculated, it is this one, and rotor copper losses they have already given to us, that is 700 watts. So the power converted will then become 37.9 kilowatts. Now for the part C, let's see what they are asking in part C. The output power P out. So the output power is actually this power. Now we are moving through this. We have already calculated P converted. So we have to subtract windage losses, friction and windage losses. Stray losses are negligible. So we can easily calculate this. P converted minus friction and windage minus 0. These are the stray losses or the miscellaneous losses. And this will actually become P out equals to 37.3 kilowatts. And after once we have this, the output power, and the last part states that let's calculate the efficiency of our motor. So the efficiency of our motor will be, we know that P out over P in into 100%. So P out we have calculated this, P input we also calculated, that was 42.4 kilowatt. So the efficiency of the machine will become 88%. So I hope it helps. Thank you.